also analyze a little bit of the sharing economy. This will be a tag team approach. So I'll start for the first 45 minutes or so, and then my colleague Anastasios Noulas will do the second part, and we'll switch over. So you can get the slides and all the code in the GitHub over there. I'm going to cover a bunch of stuff, so it's going to be relatively quick. It will help, if you want to follow along, it will help if you have the Twitter shapefile, URL parse, Foursquare, request, beautiful soup, and also network X installed, just in case you want to follow along. If not, I'll try just and describe more or less what we'll be doing and how it's going to work and what. So you're all familiar with Twitter. As you know, tweets are limited to 140 characters. This does not mean that we cannot squeeze a lot of information into them and that we cannot get a lot of information. And in particular, most of the interesting stuff is actually not in the tweet itself, but in the metadata that's associated with the tweet, right? So here we have an example. We have the author of the tweet, in the case is me. We can have hashtags, you can have URLs. You can see who retweeted it, how many times was it retweeted, so you can observe how the tweet is spreading through the network. You can see when, and you can even see where, so you can have geolocation information, which of course is what we're interested in here. When you actually connect to the API, and we're going to see that in a second, what you get back is basically a big dictionary with a bunch of keys that has a huge amount of information, right? So for a tweet that can be at most 140 characters, the full tweet object that the API returns to you can be up to 3 or 4K, so it's a lot more information, right? And in particular, you have a lot of information about the user, so their username, even their profile background image, the colors on the website. You know everything about the user, or at least anything that Twitter knows. You, of course, also have the text of the tweet. You have the source, and this is the application that was used to generate the tweet. So was it the web interface? Was it the mobile interface? Was it Foursquare? So in this case, it was Foursquare, for example. You have entities, which is another dictionary object that basically lists where inside the tweet you can find the hashtags, how they are structured, where they are. Yes, hashtags, user mentions, symbols, URLs, etc. And of course, you can have the geo-coding information. You can have coordinates, and there's also the geo field now is actually being deprecated and being replaced by a coordinates field that just lists the coordinates directly. So before you can actually do anything with Twitter, you actually have to create an account. After you have an account, you have to register an application, right? So you have to go to, I should have over there, to apps.twitter.com, and you'll get something like this, and you can create a new app. Right? You need to fill in a few fields. So the name of the app, a little description, a website, and this is going to be important. So this is where in principle would be where information about your application could be found, and then a callback URL, which is where after your user authenticates with the application, where it's going to be redirected to. And of course, you have to accept the rules of the road and not read them and just press yes, which is what everybody does. And in the end, what you're going to get, you're going to see something like this. Those going to list. We're going to give you the API key, which I'm covering there for privacy reasons, and the API secret as well. And then you have to generate a token, right? And to actually be able to do anything with the application, you're going to need both the API key, the API secret, the token key, and the token secret. So there's going to be 4 magic numbers that you're going to use, and this is what you're going to have to pass to the API to actually be able to authenticate, download tweets, post tweets, delete tweets, do everything you could possibly do. Right? So assuming you all have all of this set up, we can move on a little bit. So the API basics, just to give you an idea of how the Twitter module from the Twitter library basically gives you the basic interface. The way the library and module is structured mimics very closely the way the API itself is structured, so it's very easy. It is always better to keep your credentials inside the dict, so you can easily switch between accounts if you have multiple sets of credentials. That's what I do. Tweets.auth basically takes a no-auth instance as an argument and then returns to you a Twitter object that then you can then use to do all the operations. Twitter methods basically mimic the API structure, and there's missing one over there. There's 3 types of objects. You have tweets, you have users, and you have entities, which are the things you're mostly interested in. So just a quick example to see how it actually works. If you're following along with the GitHub repository, this is the name of the file that actually has this code. So the file names will always appear over there, and they'll always be inside the GitHub repository inside the directory called part1, because then the other directories belong to Anastasios. So the idea is very simple. Like I said, I have a dictionary with a name that is just a representation of this set of credentials. And associated inside this name, there is another dictionary which lists API key, the API secret, the token, and the token secret. Of course, you have to replace here where it says API key, etc., with the actual magic numbers that you get from the Twitter website. And then it's very simple. You just select the account you want to use, and you pass the information to the OAuth object, to the OAuth method, and then that returns an OAuth object that you can use to authenticate with the Twitter directly, right? And if all goes well and the world doesn't explode, now you have a Twitter API, what I like to call a Twitter API object, that you can then use, that you're going to use for everything else. Right? So far, so good. No questions? Yes. I'm sorry? Yes. Let me go back.
Can maybe give some time to people to look at it and download the data.
Yeah. Yes. So here is the GitHub. Sorry. Oops. So if you go to github.com under my account PMT Goncalves, you find mining georeferenced data. Sorry if I'm flying too quickly. Yeah.
So basically, you need to download the directories that are there, and then you can run the code directly to the terminal.
Mm-hmm. Yes.
There's some data.
So the piece of code that showed there was a room for accounts. Do you need Twitter accounts?
Yes. This basically the way this works is it's like as if you are using your own account to do things. Right? So and that limits also what you're, in some cases can limit what you're able to see. Like if I have a private account which means that only people who I authorize are following me, and you try to access my account using the API and you don't follow me, so I never authorized you, you can't see it. But if you do follow me, then you can see it. Right? So it's almost like you're creating an agent, a software agent that's doing things for you. So it's a cool way of thinking about it. So far, so good? Excellent. Now let's jump forward to where we were. So this is the basic structure of how you authenticate, right? You need the four magic numbers that you can always put in this order. And if you have basically a dictionary with different accounts associated with different names, and you just want to switch between accounts, it's very simple. You just switch the name you access from the dictionary there, and everything else works the same. So now, how do you search for tweets, right? So you finally authenticated, you did all the things, now you want to actually get data. Right? So you want to search for tweets, and in particular, you want to search for tweets referring to some specific keyword, let's say. So, and the way you do this is using the method .search.tweets, okay, searching for tweets, and you can see that it matches basically exactly the structure of the API documentation. So it's a get method, search, and then tweets, so you get .search.tweets. And this means that you're doing using this Twitter API object, so you do Twitter API, .search.tweets, then whatever query you want, and then count is how many results you want to return per page. The maximum number is 200. And if there is more results after that, you basically have to look up the URL to use to get the next page of results, and you can go back into the past like this. The way the search works is it basically starts searching now and back in the direction of the past. It's limited to, I believe, a maximum of 7 days, so you cannot go further back than 7 days ago. And after you start searching it, it will not update with future results. So it will just only go back in the past. So to see this, how it actually works in practice, so now the file you should be looking at is search_twitter.py. The beginning of the script is always the same. I'm just selecting the right account, authenticating. So I try to make each script completely self-contained so that you can use it as if you just want to search for tweets, you can just replace the query there, and this will just search for them directly, and you don't have to change anything else. Of course, you need your own credentials. And I should have mentioned that I'm keeping basically all the account information in this little file called Twitter accounts, and that way I don't have to worry about showing you my credentials directly. And you can just update that file with your own credentials. Yes. So while true just means keep going until there's no more results, searching for the next results, and if there's no more results, then you just stop. So whenever there's an error, you just break out. And here, what this will give you is just basically a list with all the tweets that it found. And in this case, we're using so we're searching for tweets that mention Foursquare for some reason, and then we're looking to get at most 200, which is the maximum that you can get. By default, I believe it's 25, so you want to get 200 to get as many results as possible. Does this make sense so far? Excellent. So, of course, searching into the past is not always what you want to do. Most of the time, and the most interesting thing you can do is actually stream data. And what this means is you tap into Twitter and you get a real-time stream of what's happening in the world, around the world, that's seen through Twitter. Right? So for this, you need the streaming API. This is slightly different than the normal API we just used. This gives you, of course, real-time data subject to filters. And then, of course, you can filter based on different things. In this case, instead of generating a Twitter object, you generate a Twitter stream object. So you do the .Twitter stream auth and then the Twitter auth API over there. And then to filter, you give it a query under the keyword track. And this will return tweets that match the query queue in real time. So if we did the same thing we did before, search for Foursquare, instead of showing you tweets mentioning Foursquare, going back into the past, it would start now and keep updating you every time a new tweet with Foursquare came. Of course, this is limited to API rate limitations and how much Twitter is willing to give you. But basically, after you do this, what you get is a generator that you can just iterate over and get more tweets. So let's look at the... Yes. So you can also search for user profiles. So if you want to know more about the user, or if you can get more information about the user. So here we're looking for two users, Goncalves and Noulas. The way it works now is that the keyword that you're using it and what you're searching for is basically a comma-separated list of screen names. So in this case, Goncalves and Noulas. You do API users lookup, and that's the documentation, the Twitter documentation for users lookup. Again, you can see that the structure is exactly the same, so it makes it very easy. And you just say, OK, I'm looking for screen names, and give it screen names. You can also do this with user IDs. These are the internal numerical IDs that Twitter uses. And you can give them just, again, a comma-separated list of user IDs, and it would work the same way. But here, instead of saying screen names, you use user ID equal a comma-separated list of user IDs, and then what you get basically is the same thing. So you get an iterator, and then you iterate over them, and you say this user, and here I'm just printing a little statistic and say this username has this many followers. That's it. So moving on. You can also look for social connections. So you can look for the friends and the followers of a user. Here I'm going a little bit faster because it's not the main topic, but it's interesting to know. You can get the friends IDs and the user IDs. These methods are particularly interesting because you can get up to 5,000 user IDs very quickly. So it won't give you any information about those users. It will just give you the numeric IDs of those users. Right? So if you just want to know who this user is following, you can do this very quickly. 5,000 seems like a big number, but when you think that many users you're interested in have millions and millions of followers, these 5,000 are not that many when you think about it. And what this gives you back is a dictionary with a few fields. It gives you the next cursor string, the previous cursor. And so the next cursor string is basically how you get the next page of results. If the user you're querying has more than 5,000 followers or friends, the IDs is basically the list of followers or friends, depending on which part you're querying, and the results next cursor just gives you the next page of results. And you can just ask for the next page basically by doing this. You query again the same thing, and now you give it a cursor with the results next cursor, which is what the information you get from there. And if cursor is 0, means that there's no more results left. Questions? No. OK. So a simple example on how you do this. So again, you do the authentication. Now we're looking for Stephen Wolfram. Start with cursor -1 means start at the beginning. I'm looking for followers, asking for followers of this screen name, starting with cursor here means -1, and while the cursor is not 0, so when the cursor is 0, it ends. And this is just giving me updating a list with all the follower IDs. Right? And this I forget how many followers this gives you, but it gives you a lot. Also interesting, especially when you find users that for instance, you're trying to find users that have geolocation information, because that's what we're going to focus in a second, and you're trying to see where the users have been. So you're trying to follow the users over time. Right? One thing is very interesting, you ask for their timeline. And what the timeline is basically the list of all the tweets that person has ever posted. Now here there is a limit to 3,200 tweets. Twitter will not let you go further back than that. If the user has, for example, 5,000 tweets, it will give you the last 3,200 tweets. It will not go below that. You can sometimes get less than 3,200 if the user, for example, deleted tweets, and then you will get a few less, but the maximum you will ever get is 3,200. The way it works is exactly the same. So again, now we have statuses user timeline, because statuses is how Twitter refers internally to tweets. So you're asking for statuses, user timeline, basically means the timeline of a specific user. Include retweets true means, do you want to see what the user retweeted as well, or only what the user posted directly? Of course, if you put include retweets false, you will get less tweets because it would just filter out all the retweets. Count again, 200 is the number of tweets you want to return in each call. 200 is again the maximum. Trim user true means you do not want to receive the user object with every tweet that you post, because it's always the same user, so it's always the same object, so you're not interested in that. So you can just say no. You can just say trim user equals true, and that will not include that information, and that basically saves you bandwidth. And maximum ID is basically, you can limit what is the maximum tweet ID you want to see, and this is how you go back in time, when you go back in the timeline. This will return at most 200 tweets in each call, and you can get all the user tweets up to 3,200, and only up to max ID. So you can see this in practice here. So again, we're just logging in. Now we're looking for me. You want 200 tweets, trim user true, because we don't care about user information, and you want retweets true. So this is a way of basically supplying all the arguments directly to the API calls. You just do ** args, and that will just unfold this, and it's the same as having count equals 200, trim user equals true, etc. Just for that, and then you start with a list, and you just keep adding stuff to the list, basically. That I'm doing. Yes. Is this in your GitHub? Yes. It's. Oops, I forgot to put the file there, but it should be there. Yes. Unless I forgot to commit it, but I think it should be there. Yes, and of course, since we're getting all the Twitter user, all the tweets posted by a user, you can also see who this user is interacting with, right? So you can see who is mentioning and who is retweeting, and this, of course, is only true if you include retweets. Again, you're doing the same thing. You're searching for getting the user timeline, tweets new equals tweets, and you're doing the same thing. But now, afterwards, you just go over all the tweets, and if it's a retweet, you basically see who that user retweeted, who is the other user that was retweeted. And if it's a reply, you can see who it was replied to. So you can see basically the interactions of these users, so you can see who this user is talking to and who this user is retweeting, which gives you an idea of basically on what is the social structure and the social activity of this specific user, which can be interesting in many contexts. So this is how you look specifically for a user. I already showed you how to stream data in general, but now what we want actually is how to stream geolocated data, because that's the most interesting thing, right? So stream API, yes. Oh. Yes, so this is how. So basically, this is again how you stream the data. This is just an example. You're querying for Justin Bieber, because Bieber is people are always talking about Bieber, so that's the example I always use, because there's always stuff happening. So you never just run and not get any results. And here what I'm doing is basically for the results I'm getting, I'm basically printing just the text of the tweet. So if you run this, you'll just see a long stream of text coming up in real time. And this is what people are saying about Beaver. Now, if you want to specifically look at geolocated data, then you want to see, okay, the streaming API, again, will give you real-time data subject to filters. You do the same thing. So this is exactly what you just said a few minutes ago. But now what you want to do is you want to filter by location, right? And so to do that, the keyword you need to use is locations, and then you have to give it a bounding box. So the bounding box is basically a set of latitude, longitude coordinates, basically defines a box of results where you're interested in. So this, for example, if you give it minus 180, minus 90, 180, 90, we'll give you the world, because you're defining the minimum latitude, the minimum longitude, and the maximum latitude and maximum longitude you're interested in. Or if you're just interested in New York City, you can just give it minus 74, 40, minus 73, 41. One thing you'll notice here is the convention. So it's longitude, latitude. And you can think of this basically as being XY coordinates if you think of it in terms of a plot, right? So, which is the exact opposite of what you'd use normally, because you normally say latitude, longitude, and not longitude, latitude. So you have to be careful about it. Many times you get in trouble basically by switching the numbers and then nothing matches. Now, if you do that, then you just, again, I'm going to do exactly the same thing. Authenticate. This is the query we're looking for. Just looking for New York City. We're going to stream results. So now I'm giving it a location equals that query. So I want tweets happening or referring to this area here. I'm just counting them, and now I'm just going to store them in the file, in a zipped file. So for each tweet I get, I update my count. I look at the tweet ID, and I'm just printing the tweet ID, and then I'm storing the tweet inside that file. And then after 1,000, I'm basically quitting. So this is we just generate a few tweets, store them in the file, right? And actually, if you look in the repository, you'll find this file, and I ran this last Sunday, I guess, up to 10,000. So just to give you a few tweets that you can look at. Excuse me. So you can, of course, yes, yes.
So you mentioned earlier about the limit of 3,200. So
yes, for the user, that is for the user timeline.
so
right? Here you do not have the limit for 3,200, right? Here in principle, you will get all the tweets. Well, you will get a never-ending number of tweets. Let's put it that way. Now, depending on what access level you have, you'll get more or less. In general, if you do nothing, you just create an account today and you register an application, what they give you is the basic access, which is 1%, corresponding roughly to 1%. And what this means is you get roughly 1% of all the tweets. So they just sample down.
But you can be sure if it's random or not, right?
You cannot be sure if it's random. I'm reasonably sure it's random. I've never seen anything that's showing that it's too biased one way or the other. But so you can more or less assume that for every tweet that anybody posts, you have a 1% chance of getting that tweet. It's not exactly like that, but of course, you can also buy higher access. You can get the Deca hose, for example, and that gives you 10% of all the tweets. Or you can get the Fire hose and you get everything, but those become very expensive very quickly. Like tens of thousands of dollars a month, expensive. So, and this will give you a bunch of tweets in real time, restricted to this location. This is just a little simple script I wrote just to plot them, just to see where the tweets are. So we were searching for tweets inside New York City within that bounding box. You will remember, yes, so the bounding box is between minus 74.40 to minus 73.41. So it's basically 1 degree by 1 degree. This will just basically open that file, extract the tweet, look for the coordinates, and then just plot it using matplotlib by plot. So just the simplest thing you can do, and I use that just to basically generate this figure. Right? One interesting thing you'll notice about this figure is the range. Right? The range is much larger than what you expected. Right? You asked for a 1 degree area somewhere around there, and you got a bunch of stuff everywhere else. And the reason for that is because Twitter is a bit sneaky about how it selects which tweets to give you. Now, you say we want tweets referring to this bounding box. that does not mean that it will give you only tweets that happen inside that bounding box. It will also give you tweets that somehow refer to that bounding box, which is a bit strange if you think about it. So these are the tweets that actually have GPS coordinates. So these are the actual coordinates that are associated with that. But for instance, if, like I do in your profile, you mention you live inside New York, you live in New York City in your location field, and you post a tweet with GPS coordinates, Twitter might give that tweet as well because it thinks that might be interesting to you. And even though I'm not necessarily, when I'm tweeting in Portugal, for example, I'm not inside New York City, but it will still show up there. So you would see a dot somewhere over there saying that guy's in New York City, right? So you get a bit messy here. Yes, back there. These are all GPS. Okay? Now, the reason why Twitter selected these guys over here, for example, was not because the GPS was inside that bounding box, but because there was other information in the tweet that referred to that bounding box. So Twitter is more generous about the way it does, right? Yes?
So to filter that out, you can just filter the coordinates that come in the URL parameter, right? So you get your tweets back after doing your query. And then
That's exactly the next step. Good job, good job. I should pay you off. I should pay you a coffee later. Now, how do we filter this out, right? Now, the way you define geographical boundaries in general is you use shapefiles, right? You can actually go to that website of the New York City government and download the official shapefile that gives you the boundaries of the boroughs of New York City, right? And it looks something like this, and it basically defines everything, the official definition of what New York City is. Oops. Yes. This, unfortunately, they're not using the right projection. They're using a different projection. What we want is what we call here the WGS84. Yes, WGS84, which is basically latitude and longitude, defined on the grid defined in 1984 that defines basically what latitude and longitude is around the world. You can convert it. Here this is a very simple exercise. You just open it in your favorite GIS program, and then you just save it as, and you change the coordinate system before you save it, and that would just generate another file with the right coordinates. To save you the trouble, I downloaded the original files, I converted them, and you can find them all in there. Yes?
there are also command line tools you can use if you want to
Yes.
know this.
I'm not very familiar with them, but I know they exist, like OGR to OGR. Yes?
What is your favorite JS program?
QGIS.
JS.
And it's open source, and you can use it for everything. Of course, the official one is ArcGIS, which is extremely expensive and only available on Windows. QGIS does like 95% of everything you could ever want. So, and it's much more lightweight. But in any case, for this example, you have all the files you need there. The original files are called NYBB_15C, I think, and or just NYBB. And then the ones with the modified coordinates are NYBB_WGS84 or something like that. So you can see the distinction easily. Now, if you have this, and what you have is basically an arbitrary polygon that defines the area you're interested in. There's a little library called PyShape, or PyShapefile, if you want to, that basically defines utility functions to load and manipulate shapefiles programmatically. And yes, still have a little bit of time. So the only thing you really need to know about this is how to read the file and how to get the records. That basically tells you what are the polygons that are defined, and the shapes basically gives you all the shape information you need. And before you can use that, you need another library called Shapely, and Shapely basically gives you a way of defining geometric objects and simple operations on these geometric objects, right? So it can define points, polygons, multi-polygons, shape, that is a very simple way, which is what I'm going to use to basically generate the right polygon based on information that you get from other places. And it can give you a very simple way of calculating other things. So you can calculate what is the centroid of a polygon, if one polygon crosses another one, if it's inside another one, etc. If it's within another one, if it touches another one. Also, and there's many, 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 many more. Here are just a few of them. So how do we actually do this? this is just an example of how to actually load the shapefile. So again, so you just open it there. You see you found 5 records. And then you just go over all the records and that show the name. So this is a real simple example. So if you run this on the shapefile I gave you, it will list basically Staten Island, Brooklyn, Bronx, Manhattan. Yes, and then it lets you select one. So here I will just use the command line, and then you just select the one you want and say, okay, if it didn't find it, it didn't find it. And if it found it, it says, okay, I'm going to use that one. And then calculates here I was going to select Manhattan, and then I was just going to check that the centroid of Manhattan was inside Manhattan, just to exemplify how you can do this. Right? Now, you can also use that to actually filter the tweets directly. So looking again on the file, here again I'm going to use the file I just used before that I just gave you of the NYC tweets. Here I'm opening the shapefile directly. So I said nybb_wgs84, which is a modified one. Again, it will find 5 records. I'm going to select 2, which corresponds to Manhattan. Here I'm going to print the list of records again, and you say, okay, we're going to use Manhattan. Select Manhattan, and then open another file. And then for each tweet in the New York City file, it will check if it's inside Manhattan or not, and if it is, it will save it to the Manhattan file, right? And if you do this, after you run this, you'll get another file called manhattan.json.jz, which is already in there. And if you plot it, you get exactly what you would expect. You get only coordinates inside Manhattan. Right? Now so far what you have is you have a way of searching Twitter, finding the tweets you're interested in, filtering even by location. I should have mentioned, I didn't really mention, that if you search for a specific query and you search for a location, it doesn't actually do the end of the tweet, gives the or. So it will give you things that match either the query or the location. You cannot do both. So you have to do 2 steps if you want to do both. So you could search for a specific query, like Foursquare or Justin Bieber, and then filter out the ones inside the location. Or you could search for a location and then filter out the topics you want by hand. But you can't do both at the same time, because it'll just give you the or of all the filters you apply. And here you can see that the coordinates are, of course, are correct, and you can basically recognize the map of Manhattan. So, and this basically gives you a big overview of what you can do with Twitter and how you can get geolocated Twitter data, process it, and analyze and extract what you want. Right? Now, another big source of geolocation data is Foursquare. Right? Foursquare, of course, is a check-in, is a way for you to advertise your check-ins. So you say, okay, I'm in this location right now, which of course started more or less within Twitter, the Twitter ecosystem, and then branched out. What you generate with Foursquare are basically check-ins. So you say, this user checked in at this place. Again, you can have a little, basically what corresponds to a tweet. You can see how many people liked it. You can have, of course, URLs associated with it, etc. Again, when you connect to the API, you get an object with a bunch of information, a lot less information than in a tweet, but that's okay. Venue basically gives information about the place where the check-in is occurring. Entities, again gives information about URLs, etc., that are inside the tweet. Now the text of the check-in is called a shout, and that's just the text. And the likes basically tells you how many people liked it. It does not give you information about who liked it. Again, if you want to do something, you have to actually create the Foursquare account. You have to register an application, and this will generate, again, the magic numbers. Here it's a little bit trickier. You actually have to give it a redirect URI. So this is where it's going to redirect you after you log in with the application, well, where your user would be redirected to after they logged in with your application. And this actually has to work. That URL has to at least exist in some fashion, because it's going to use it in a second. To actually register the application, it's a bit trickier than it was before. So now you have the client ID and the client secret that you basically get from here very easily, just by clicking register an application and filling out a couple of fields in this form, which are basically URLs and a little bit of and a name of the application you're using, or rather that you are creating. So now that will give you the client ID and the client secret, which are two of the tokens you will need. But now you need the actual token that you're going to use to do everything. Right? So the way to do this is first you need to request an auth URL, which is basically the URL which you're going to supply to your user and say, okay, log in now, and then the user will log in there. Of course, you don't want to actually do that. You want to do it automatically. So you, using the client ID and the client secret, you can authenticate with the API. You can ask for an authorization URL, and that gives you a URL. And as before, I'm going to put all of basically this dictionary inside the Foursquare accounts Python file. And again, all this code is inside the auth URI Foursquare. Now, if you open the URL it's giving you in actual browser, you're going to get something like this, and you say, are you okay authorizing this application to access your account? And then you press OK. And that will redirect you to the URL that you selected in the beginning when you were registering the application. Right? Here, of course, the URL doesn't actually have to exist, but something has to be there. And it's going to give you a big magic number hiding in the URL over there, which is hiding between the equal sign and the sharp sign. Right? So it's all that part that's selected over there. And this is the last piece of the puzzle. Right? After you have this, with this magic number there, you can ask for an access token. And you only need to do this once. And after you have the client code, the client token, and the access token, you have everything. Now, the reason why here you need three pieces of information, for Twitter you needed 4 pieces of information, is basically because Twitter is using OAuth 1, here you're using OAuth 2, which are different and can be used for different things, and have different trade-offs. One of the advantages of OAuth 2 is just with the access token, you can do everything. That's all you need in the end, most of the time. And the advantage of this is that this token is basically given to the application by the user, and the user can revoke it at any time. You can even assign expiration dates on access tokens so that they go away automatically, etc. So you should really, if you're interested in that type of stuff, you should really read up on OAuth 1 and OAuth 2 because they're really interesting. Now, to actually authenticate with the API, you do exactly the same thing, similar thing to before. You select the account information. Again, the account is inside, dictionary is inside the Foursquare accounts there. You provide the client ID and the client secret. You set the client token, and then you can start searching and using Foursquare to extract information. Questions? No. I saw somebody raise their hands. This is much simpler and intuitive. It's less prone to mistakes, and it automatically takes care of all the details. Right? You can just do this very easily. Now, there are 2 main types of objects. You have users and the venues, and so people and places, if you want to think about it. And there's many things you can do that users can do on venues. They can check in, they can like, and they can leave tips. Right? So they say, like, in this place, you should try the steak. It's very good. Now, because of API limitations, in the beginning, they were a lot more generous. Then they stopped being so generous. So they limited it a little bit. And the reason for this is because of privacy concerns. And in the beginning, they were very generous. And then people came out with stalker apps with please rob me and say, OK, look, this user is not at home. So you should advertising, that type of thing. And so they changed the API to reflect this. So what this means is that it's very easy to get information on users and on venues, but it's very hard to say this user is in this venue. Right? They're trying to keep the 2 things separate. So venues, of course, correspond to physical locations. They're the most important object in the Foursquare universe. They are very generous. They give you 5,000 requests per hour, which is a lot. If you do the client object dot venues with the venue ID, it will give you a venue object, which again has a bunch of information. You can even get tips that were left on the venue. You can see who is there now, or at least some information about who is there now. Venue similar will give you a list of similar attractions as defined by Foursquare. The way they define similarity is not always clear. Venue search means that you can search for places near a location. So you can search for pizza near Times Square, and it'll give you a list of pizza places near So this is an example on how to find similar venues. So again, you're just doing the authentication thing. So up to here, it's exactly the same thing. Then this is the venue ID I'm looking at. I'm using the client object to access the venues. So I give it the venue ID, and that gives me the venue information. And here I'm looking for similar venues. So I'm saying, okay, with this venue ID, give me similar venues. And that gives you a list of similar venues. And here I'm just asking for the venue object just to get information, a little bit of information about the venue, because that looks like a magic number. And if you run this, you will say, okay, similar venues to this one are, and here's a list of them. Right? And that venue, if I remember correctly, is like the Empire State Building. And of course, if you can just run the script and see it in real time. Now, tips. Users can leave tips in venues at any time. This means that they don't need to check in. You can leave a tip on Mount Everest right now, even though you're not on Mount Everest. Reduced tips for a venue can be accessed to use venues tips. So reduced tips means that they don't give you the entire tip object. They just give you a limited set of information. This is limited to a maximum of 500 per call. So what you'll get from here is at maximum 500. If there are more tips associated with that venue, then you can use the count parameter and the offset to basically go through the list and get more information. The full tip objects can be obtained using the tips interface directly, and you can get the documentation over there. And these contain reduced user objects that are public and basically give you a simple way to connect users to venues, but with some limitations, as I mentioned already. So this is how you actually use it. So this is the tips foursquare.py script. Again, you're just authenticating over there. This is the venue ID. Now we're asking for tips. This gives you the list of tips and how many tips there are. And I keep looking for more tips as long as there are tips to look for, and adding them all to the list, and then printing them all out, basically. So it's a very, very simple code just to highlight how you can do this. Now, I'm almost done with my part. So, check-ins. Check-ins, of course, are the most important thing on Foursquare. They're the reason why Foursquare exists is to allow you to check into a place. It's a way of connecting users with venues and give you variable temporal demographic information. And this is basically the information that I'm assuming Foursquare sells to their customers. .check-ins, the check-in ID will give you the check-in object. If you use the user's interface to look for check-ins with the user ID, this will give you all the public check-ins for that specific user. Of course, in many cases, there won't be that many public check-ins because of privacy concerns, as I mentioned. Or for all check-ins, if a user ID is your friend, right? So this goes back to the same thing with Twitter. It looks at who you are and the person that's authenticating you. And that's why you need the user information. So you need an actual account on Foursquare and not just an API account. So the way it works is the same way. You authenticate, you use a check-in ID, and now you use the check-ins interface to get information. You can also get information about the user. And you can see, if I remember correctly, this check-in ID was done by Barack Obama, because it's like one of the public check-ins I was able to find some time ago. So of course, everybody wants privacy, but not too much privacy. And in particular, people like to show off and basically tell their friends where they are. So Foursquare somehow had to increase the privacy, but also decrease the privacy, which is kind of weird. So the way it works is users can have the options of sharing their check-ins through Twitter or Facebook, right? So I can check in on a place on Foursquare. I'm very self-conscious about my privacy, so I don't allow anyone on Foursquare other than my friends to see it, but then I publish it on Twitter and everybody can see it. The status text is shared along with the URL to a web version of the check-in. Since to actually be able to pass through the privacy barrier, you actually need the access token, but you don't want to give an access token to everyone, so you create a new special access token that only works for this specific check-in, and this is called the signature. And each signature is valid just for that check-in for that user, and no one else. So it's a single-use token. So this is what a check-in URL looks like when it's published on Twitter or on Facebook. So it's basically foursquare.com or SwarmUp now or whatever. The user ID, check-in, the check-in ID, and then the signature information there. So something like this. So this will correspond to the user TIIIA, I guess, performing this check-in and has this signature. So if you use the check-ins interface with a check-in ID and give it the signature as a parameter to the function, then basically you can get you can access that page and actually see what the check-in is, right? Of course, to do that, you actually need to be able to get these URLs. And the way you get these URLs is through Twitter. So you search for Foursquare, or you search for geolocated tweets. Inside those, you find the ones that have basically Foursquare information, and then you just need to extract that information from there, right? So this is how you would parse a URL. So again, this is the URL that I just showed you in the previous slide. You can parse it using URL parse, extract the check-in ID basically corresponds to the base name. The query will basically give you what the signature is, and then the screen name is hiding inside the path that you get, and using that, you can just get the check-in directly. Right? And that's magic. And potentially against the terms of service of Foursquare, depending on who you ask. Yes?
Wait, so these signatures are not based on the app ID that's accessing it?
No, this token is basically a token that's generated by the user when they check into a place and say, okay, I'm allowing anyone that has this token to see this check-in, right? They're not connected to you in any way. Now, the problem with doing this is you're still going through the API, which means that you still have all the API limitations and you're still limited to X number of check-ins, etc. The way to do that is not go through the API at all and basically go through the web interface, which again might be against terms of service. So you use the requests library to open the URL that you just got from Twitter. If you want to authenticate using user and pass, but that's just generic information based on authentication. This is generic information about the requests. Requests will return after you connect to a URL. You open the URL. It's going to return you a bunch of information about the connection. It's going to say with the status code, okay, was it able to connect and obtain the page? So is the status code 200 or not? The text is basically the HTML. The URL gives you the final URL. So if you have a URL shortener, this will be the complete unshortened URL. Even if you have multiple URL shorteners, it will just navigate through all the shorteners until it gets to a final page. And that will give you the information. And the .json, if the document on the other side is JSON, this will just give you the JSON object directly. So this is an example on how you could use this in general to authenticate, which is not particularly interesting here, but it's important because it highlights the idea that you can provide headers. Right? And these headers are a way, basically, of you providing extra information to the 2 minutes. No. Provide extra information to the server so that it can handle your request better. Right? And in particular, since you're trying to get around all of these limitations, you can use this to spoof your user agent. So instead of the server looking at the request and saying, "Oh, this is coming from Python," you can pretend that the request is actually coming from, in this case, Firefox, I believe. So you can provide the user agent like that. And this is just a little simple code to show that if you make the same request while spoofing the header or not spoofing the header, you will get different results. So in the first one, you will get whatever Python library version you're using. In the second one, you'll get exactly that piece of text over there. And this is just a simple website that if you open it, it tells you what is the user agent you're using. So what is the browser you're using. Now, finally, I think this is my final slide, yes. So this is how you actually do all of this. So if you have this URL that you obtain, let's imagine from Twitter, you want to pretend to be Firefox, you're going to connect using the requests.get method to that URL using that header. The final URL is basically the URL after all the redirects, which you're going to need to extract the signature and the user information and the check-in information. So just like we did before. Here I'm using Beautiful Soup basically to parse the HTML of the check-in page that I'm getting. And then I'm extracting basically the screen name of the user, the venue information, and just printing a little message saying, okay, this user checked into this place. And Again, you can find the code on beautiful.py. And if you don't have any questions specifically about this, I'm going to tag my colleague in. And that, yes?
I have a quick question about going back to Twitter. They changed it so that like the geolocation is by default turned off.
Yes.
So anytime you tweet, there's no geocoding.
Yes.
So most people won't volunteer to turn that on. They don't.
Yes.
Report it. So have you found a way to gather that geolocation data through other means, whether it be the content of what they're talking about, maybe who they tag, things like that?
Yes.
Any approach?
Yes, there are many techniques to do this. I'm very limited in time, so I didn't really go into them. He's going to talk a little bit about that. You can look basically at, you can try and parse the location field. Location is something you type by hand, so it can be not too reliable, but you can parse it directly. You can look exactly at what they're saying, what they're mentioning. Twitter will try to add some geographical information if it can. And that's why when I showed you the things that were matching New York, it's showing things even outside New York because it's matching the location field and try to say, okay, if the location field is inside New York, then maybe I should show this as well. So Twitter, on some ways, is trying to compensate for those things, right? Which is kind of like Foursquare trying to give you privacy, but allowing you to share your things at the same time that you want privacy, which is kind of weird. No. No, Beautiful Soup, I didn't really go into the details, but basically what it does is it parses HTML or XML. And it's not really a dictionary, but you can kind of treat it as a dictionary in some cases. But there's a world, understanding how Beautiful Soup works is another whole other world that I didn't really have too much time to go into. But basically, if you replace the URL, this will parse it exactly and will give you the information. So you don't really need to understand soup too much. And without further ado, Anastasios Toulas.
Thank you. So that's pretty heavy.
Let's try without it. So can you hear me at the back? Yes? No? Okay, I have no. No, you need a mic for the. Sorry, I forgot about that.
Okay. So hello everybody. I will continue from where Bruno left. So it's nice to collect all this data, but what can we do with it, right? So we will cover several analysis and mining aspects of this georeferenced data. So I'm based at Lancaster University. I'm an associate professor there. I had a pass from Foursquare a couple of years back, and I have to thank University of Cambridge for sponsoring my talk, for paying for my trip here. Let us start. So though this is London, its yellow dot is a Foursquare place, and we saw a sample of them. And what we will be studying in the first part of the talk is essentially a network of places. So as users move between one place to the other, they effectively connect them. And the way people have been studying social networks, studying friendships between people for the last 10 years, our message here is, can we switch our perspective to places now that location-based services and the sharing economy services like Uber, Airbnb, and so on are rising, and try to see what this type of network can tell us and where it can be useful. Of course, this data is not only about static representation of places, but we have a notion of the category of places. So red here is arts and entertainment in Foursquare. Green are outdoors, and the size of each circle is proportional to the popularity of it. Right. So let me cover your last question and show you a trick on how to acquire check-in data abundantly and publicly. So if you go on Twitter and search for shoremap.com, this is the actual check-in app of Foursquare. You can see a number of live tweets with check-in information. So every tweet has a URL that points then to the SORM website, where you can get information about the place, the category, and the user that has checked in there. And the nice thing about this is when you search Twitter by specifying a string query, then you get effectively all the tweets that are associated with it back at a given point in time. Right? So let's focus on practice now. So we'll be studying place networks as we mentioned. So if you go on GitHub and you download the place network live directory, there you will find the code. You can run the code through the terminal by doing Python network analysis.py. The data is there, so we have two data sets. One, it's a network connecting places, a four-square network of places, connecting by means of user movements. And then for every place, we have geocoordinates and the title of it. And the title, for example, this is a conference venue for PyData, will be used to allow us to interpret some of the observations we make on the network. Right. So this is a library which I hope you have installed. It's Network X. It's very easy to install, by the way. So if you download it now, you can just do Python setup, install, and it will do the job for you. But effectively, what it is, it's a library that contains a lot of utility functions and methods for modeling and analyzing networks. So let us start. So to begin with, we need to load the nodes of the network. In our case, the nodes are places. So I have included a file in the folder where we have a list of 4 square places. They're approximately a sample of 2,000 public places in New York, anonymized by ID. And what we can do is basically parse this CSV file, and for every place get latitude, longitude information, the title, an ID, and then effectively store this information in a dictionary that we will process next to model the network. Right. So I have included here a visualization. So how do we define this directed network? Directed means that an edge has a directionality information included in it. So a user might go from the cinema to the hotel, or to the gambling place, or from the disco to the cinema, although that's not very common. But anyway, in the end of the day, we have a place network, right? That we can use network X to read it, basically store it as a sort of like variable. And then we can start calculating statistics about it, right?
A directed edge is a subsequent check into the same user.
Yes. So, and we also we impose an 8-hour threshold. So to make sure we don't have check-ins that are 3 months apart, okay. And we have consent. So we have applied the filter with respect to time. And important information to extract for the network is basically how many nodes there are there, how many edges, so the order of the network and the size of it. And of course, then we can print this information and we can see how many nodes we have in the network. So if anybody has run it, maybe they can tell how many you got.
1775.
That's a good one. That sounds approximately what I had there. And then the average degree is a sort of like a very sort of like is a representation of picking a random node in the network. What would be the expected sort of like number of edges that it has, right? How well connected it is. However, we will see that this is not a good approximation of what you see empirically in the actual network, because taking average in this sort of like context doesn't work so well. So I will talk about this in a bit, and actually we will move with a degree distribution of the network. So we take a node has a number of edges, and we want to see what this distribution looks across the network.
Distances from one node to
it's not distance, it's connectivity. So if I'm this venue, and I have 5 connections to other venues, then this is the degree of the venue. And it's a very fundamental concept in network analysis. Basically, it tells you how important a node is in the network.
So it's a distribution of how many shortest paths between that node and all the other nodes?
Direct paths.
Direct paths.
Yeah, not shortest. Shortest paths is a different notion in network, so it can include multiple hops from one node to the other. Whereas here, for example, if you have 10 friends on Facebook, I'm really sorry about you, but then your degree is 10. If you have 1,000, then your degree is 1,000.
Oh, so it shows the distribution of the degrees of the different, all the places in the network.
Exactly.
Okay.
Yeah. And that's what we are after here. And of course, we have in degree, so outgoing edges, and out degree, which is outgoing edges, and in degree, so edges that point to the node. And of course, we can use Python to read this information operating on the network object returned by network X. And then we can use matplotlib in order to plot this degree distribution. And we will see that we will use two scales. The logarithmic scale, so if you set this variable log scale equal to true, then things will be plotted on logarithmic scale. If not, then things will look like that. So that connects to the previous point of why you shouldn't be taking just the average degree in the network, because most of the values in the system, in the network system, are small. So most places have very small degree. And occasionally you have places like Penn Station and so on that will be having a very high degree. And for this type of very broad distributions, it's better to show things in logarithmic scale. So you can see, how the same data in log-log looks much better in quotes. And of course, you can operate on these curves and try to characterize them mathematically according to the slope. The steeper the slope, the most important, it's more likely that you will get a node with small degree. Right. Another important concept in network analysis is the sort of like triadic closure. So in the context of social networks, that translates to a friend of my friend is also my friend. So we tend to form triangles. And our question here is, do these place network systems also show up this important property, which we can refer to as clustering coefficient? So you can run this code basically after converting your network to undirected for simplicity. So we disregard the directionality of the edges. Then we can extract the connected components. So looking at network data, basically, you can have a set of nodes, a set of places being connected. But sometimes you can have like isolated pairs of nodes being connected that are not connected to the bigger network. So we can apply this connected component subgraphs operation using network X and get those components that are connected with each other. So all nodes connect with one another in the network. And we will take the first component by using the 0 index here. And that is called the giant component of the network. So this is the biggest component where all pairs of nodes are connected with each other, either directly or through hop by hop connectivity. So has anybody run this to report clustering coefficient here?
Can you explain clustering coefficient?
Yeah. So basically, if you have a node in the network is connected to other nodes, then those other nodes can be connected to each other or not. So in the case that they're disconnected, so you form a sort of like star connectivity, then clustering is 0. You have no clustering. There's no community there, right? But then, if they're connected with each other, then this goes up. And this is something that we observe in social networks, and we also observe actually in place networks. And it's an interesting sort of like reflection of, where we socialize and, where we go, basically. Now, if you, to take the average clustering coefficient, you have to go through every node in the network, measure for each the number of triangles that you observe versus the number of potential triangles, and then get the average across the network, right? And what you should get here is something like 0.2, with the maximum being 1 and the minimum being 0.
Okay. So it speaks to this, to how well connected the people to whom I'm connected are.
Yes, exactly. And it's the sort of like the building block for studying communities or clusters in these networks, right? Everything clear so far? I bet not, but feel free to interrupt. Oh, yes.
So if you had just like a pure like lattice of triangles, what coefficient would that be? Would that be like close to 1?
I don't know. You can code it and let us know. Right. I have to move a bit fast, right? So we talked about degree distribution of the network. So those metrics are known as centrality metrics in network. So they give us an indication of how important its node is in that particular time case places, right? And we have different type of centrality methods and metrics. So between a centrality, instead of looking at the number of connections a place has, it looks at the number of paths that traverse that place in the network. So I might not have too many connections, but given a random pair of nodes in the network, it might be the case that to go from place 1 to place 2, I have to go through place C. And if that place C is found in a lot of cases in this context, then it has high between centrality. So basically, people have been trying to devise different sort of like formulations of centrality metrics and try to see which of them would be more appropriate for their particular application scenario. So we talked about degree centrality, and we will also look at the eigenvector centrality. Eigenvector centrality is an interesting one because it tells you how well are you connected to central nodes. So you might not have very high degree, but you might have a lot of interactions with Penn Station that is very well connected. So that will raise your eigenvector centrality.
So
Yes.
compute it from the correlation matrix, basically?
From the
You compute those eigen values or whatever from the correlation matrix between nodes?
correlation matrix.
Or how do you get those eigen values?
So the eigenvalues, yeah, that's a good question. Sorry to be brief. So you use the adjacency matrix of the network. You can operate on that matrix and get the eigenvalue distribution. And then you apply a mathematical formula there that can allow you to extract the information I described, how well you're connected to very central nodes. So you're implicitly central as well. You can use, so what we get from this sort of like centrality operations here, we get dictionaries where each node has an ID, that is the key of the dictionary, and then the value is the centrality of the node. And of course, what we can do is use a utility method, get top dictionary keys. We're given a dictionary and the number of the top k most important nodes we want to extract. We can get them. In that particular case, I'm applying the 3 different centrality metrics with parameter 10. So we'll get the 10 most important nodes in New York. And what we'll do is like basically get the top 10 and we will plot the title of the place. So for each centrality metric, we will try to see what is a sort of like real world place in New York that belongs to the sort of like top 10 most connected places. Right, and this is the output. So you can see that airports tend to be at the top of the list. You can see that there is a very high correlation, at least at the top 10, in terms of the places that you find of those centrality metrics. But you have outliers as well, right? So you can have cases of, for example, the Central Park West, which is the west side of Central Park, which is a place in Foursquare, appearing in the top 10 for degree centrality, but has low between the centrality, so it doesn't appear in the top 10, and lower eigenvector centrality as well. So depending on the application that you're going for, you might want to use a different centrality metric. Everything clear so far?
So as you mentioned, the airports and other places where a lot of people go tend to be the top. Would it make sense to apply some kind of weighting adjustment to see how popular places are versus just how frequent places are relative to how many people just show up there?
Yes, yeah, I think you can do that. I think you can basically apply different methodologies, so you can focus at different sort of like subsets of nodes in the network that you're interested in. Of course, these systems suffer from the rich gets richer effect, where you have like this very sort of like dominant set of nodes that attract most of traffic and so on. But sometimes, depending on your application scenario, you might want to focus in a small neighborhood and learn something about it. And of course, you can refine these metrics accordingly. So if you look online, there are basically tens of centrality metrics that have been proposed in the literature. So the idea here is like check the basics and maybe explore on your own at your free time, right? So Network X provides also functionality for drawing your graph. It might not work very well for graphs with a huge number of nodes in the order of millions, but in the context of a city, you have usually thousands of places, so tens of thousands, which is a manageable size. So this is a sort of like non-geographic representation in New York. We basically store latitude and longitude values at the position dictionary. Position dictionary is being passed at the position parameter of the draw function. And then we can specify also the size of the node on the graph. And of course, we can store it. And if you run the code, you can get this graph, basically. And if you want to go more sort of like beautiful and hardcore in terms of like visualization, you use processing. And this is a snapshot made by a Foursquare designer. We include it in a paper where we study thoroughly these place networks. You can basically download it here and look about their dynamics. We do link prediction, so we study how the network looks at a particular season of the year, and we try to predict how connectivity will emerge in the next period, and so on. So the goal here has been to introduce these networks and hopefully make the community more aware about using them in real-world applications. And talking about real-world applications, we go to the second part of the talk. So with some friends in Belgium, we have been building OpenStreetCab, which is basically an application that has been launched in New York. We have so far 5,000 or more registered users, 1,000 active users. And basically, you can download it from the App Store or the Google Play Store if you want to see how it works. The idea is you have an origin and destination that you're willing to travel in the city. And given that Uber has been introducing the very famous search pricing, where pricing for a particular journey depends on demand, we thought it would be really interesting to compare prices with other companies. In that case, it's been Yellow Taxis. And the way we have basically search results for flights, you have different companies and different prices, and you have services on top of that. We want to do the same for taxi transport. And what we've been doing is we've been looking at trips in New York City, and we took advantage of publicly available data, which I will point to, about yellow cabs. And we exploit Uber's API as well. And for a given trip, we can ask how much you charge, take the difference, and see, in fact, that yellow cabs tend to be cheaper. So users, and this for a sample of 643 queries in our app, save on average $6 per trip. And collectively, we can save thousands. We don't make money out of it yet. So we were lucky because when we launched the app back in March, we had a few tens of users. But when the legend, the main man, Tim, picked it up, we had suddenly hundreds of users joining, and a lot of them still using the app. We are launching in London soon, and I will get to more details about that. But let's get practical and solve this sort of like very interesting task, which I think it's very topical, right? And the task we want to solve, and you might as well do it by downloading the search prediction folder from the GitHub repo, is given an area, can we characterize it in terms of like demand, Uber demand, and give it a sort of like predict a value about it that is a sort of like mean search multiplier, the average search price multiplier for this particular area. And moreover, can we use Foursquare data and yellow taxi data to do this? And in fact, the interesting thing, and I will point to a paper related to that, is that if you try to predict Uber demand using Foursquare data, you get a correlation 0.4, Pearson correlation. If you use yellow taxi data, you get 0.4, but if you combine them in a supervised learning model, then you get the best of both worlds, and you do very well, and you get a sort of like Pearson correlation of 0.8. Those are how, this is a figure showing how the search multipliers are distributed in the city. Most peripheral areas are basically having a multiplier that is 1, but as you move towards the center of Manhattan, then you have like higher demand, and you can have like search values that can even go to 1.5 on average. So Uber has a base fare, but on average, the effective charge to the customer happens to be higher. Yes?
Can you just expand on this graph? So this is a single point in time and all the search multipliers for all areas of Manhattan.
So this is for a particular period. Yes, so, and we have aggregated. So, you know, if you take one particular area, search will change over time, right? But we have aggregated to simplify the prediction task for, you know, a given period of 3 months of taxi trips.
Okay.
And then we query the Uber API, and we'll get into that.
Okay.
And we take the average of search for a particular area.
So when you say mean surge, like if there is no surge, is that included in the calculation?
If there is no surge, yes, and this is one, right? So most peripheral areas usually do not surge, unless it's an airport or whatever.
Okay.
Right, so these are, I will skip this bit, and we will move to this working directory, and I shall introduce, aside from the taxi data, which you can find in the GitHub folder, we use also Airbnb data. And what you can do essentially is basically you can get this CSV file where we have a sample of Airbnb listings in New York and store this in a Python list, or the coordinates. And basically out of all the data that is there, you have multiple fields about reviews, how popular the place is, how many people have been there, and so on. We take just latitude and longitude, because all we want to do is see if we can use how frequent Airbnb is encountered, how frequently is being encountered at an area, how frequently are taxi trips at an area, how frequently are Foursquare plays at an area, and combine those to predict search. You can download a lot of Airbnb data following that website, not only about New York. So you can look at different cities around the world. I think this is a very interesting data set. Uber has an API which you can query to get price information. So this is an example of a request. There is the uberquest.py file in the folder where you can find this method. So given a latitude and a longitude of the origin of the trip, and then latitude and longitude of the destination, we basically ask what is the price that you would charge at a specific point in time. We get the price back. And then basically, this is getting to your question. Essentially, here what I plot is basically for different types of routes. You have like the evolution of the search multiplier. So for a specific route, you have like the price changing over time. And what we do is take the average of this, and then we aggregate over all routes at a specific area.
Okay, and these are historical prices? You can query the API for
You can query the API now, but we won't collect the data now. That's why I have included this CSV file where we have areas and the average search multiplier that we have crawled in the past and calculated in the past.
So you can query for now, but you did it weeks ago.
We did it like 3 months ago.
But I can't query for something that happened 6 months.
You can query, yeah?
Okay.
Yeah, but you will get the price now.
Oh, well, that's...
Yeah, yeah. It would be nice if it was like that, no? All right, and we, here is a, I think I should move a bit more quickly, right? So we have 10 minutes and I have 7 slides. It's not bad, actually. So basically, of course, we want to split the city into areas, and Bruno showed before, you know, how you can get different sort of like border delineations within New York. Here we'll use just a grid, so you can apply a simple grid structure on top of the city. And then effectively, what we want to do for each layer of data that we use, we want to calculate the number of occurrences, and then see if this can predict the search potential of an area. So here we initialize a New York sort of like grid. That's how you can call it. We have a maximum and minimum longitude. We have a step which specifies the size of the cell. You can have bigger or smaller grid cells. And then we have three NumPy arrays, two-dimensional arrays, where we measure the number of Foursquare venue occurrences, Airbnb listings, and number of taxi trips. Here is the code that, if you run it, you will get how many of it we have in the data. And this is how it looks, basically. So what we do here is we iterate for the three different layers of data. We have the geographic coordinates of each layer. We take the latitude and longitude for each pair of coordinates. We check if the coordinates are within the grid. If they're outside, we can just discard them. And then, given a latitude and longitude, we want to find where it fits in the grid, right? So we want to find this cell where the data actually belongs to. And basically, we can augment the number of occurrences per cell for each of the data layers we have by iterating through these three data layers. Right. So here I'm getting to how do we plot the distribution of search values, right, per area. So if you run this, you will get this graph. So basically, we assume that we have crawled the Uber API. We use this average search in cell CSV file to get for every area the average cell coefficient multiplier. And then what we do, effectively, we use a Python histogram to plot all the search values. And this is what it looks like. And now what we can do is basically go through every layer that we've stored in our grid structure and ask to what extent the frequency of occurrences of values for a certain layer matches the sort of like the size of the search value. So to what extent the different layers correlate with Uber demand effectively. So if you get the data for yellow taxis, you can see that the Pearson R correlation is 0.43. For Foursquare places is 0.4. Of course, an important thing to take into account here is we have used a sample of both, and the sample matters. Here the goal is to show you the methodology. When you will get different data sets from your sources, you might get different numbers here. Airbnb listings, despite the fact that we have more listings, for example, than Foursquare places, the correlation is lower. But the goal is how can we combine this to supervised learning model and maximize our prediction scores. These are actually correlation measurements, they're not predictions, but effectively correlation is the first step towards prediction task, right? Okay. So how do we do supervised learning in Python? We use scikit-learn, of course. It's one of our favorites. And to begin with, basically, what we do is we want to initialize our training set in terms of like features and labels. So we iterate through the set of areas. For each area, we have a search value. This is the label. This is the sort of like goal of our prediction. And then in the training set, we store the three layers of information: yellow taxi trips, number of Airbnb listings, and number of Foursquare places. And then, effectively, we do testing. And testing is really important in machine learning. You don't want to overfit, right? There was a discussion in the machine learning panel yesterday about what's the best testing methodology. One of the one that I think is more appropriate to use is leave one out error. And this is known as an unbiased estimator of the generalization error in a prediction task, where effectively what you do is you have a training set, you pick one point, you take it out, and you make it your testing point. You train the model to the rest of the data, and then you try to predict basically the point that you took out. And then you iterate for all points in your data set. And this is the sort of like, theoretically, the best estimation you can have in a prediction task for the generalization error, but it costs a lot. Because you have to iterate through all your points in the data set, and if you think you have to do that and optimize your classifier for billions of points, that would take a lot of time. Here we don't have this problem, the data is sparse. So if we have like 2,000-3,000 areas in New York, then we can do this pretty quickly. So effectively what we do, that's the implementation of this process here. We set up the training data, the label data. We make sure that all search multipliers of value 1 are removed. So this is noise, essentially. If you try to include areas that have search value on average 1, then you will get too many of them with different features, and that will confuse the classifier. So if you want to get things running properly, you have to denoise a little bit your training set. And then effectively, you can train a decision tree regressor, which is effectively a regression model implemented as a tree. We have set here, through some experimentation, the depth of the tree to be 30. There's a number of sort of like branch switches. We do the fitting on the training data, and then we do the testing on the particular area that we have left out. And then we can store our predictions and calculate the correlation values. And I wonder if anybody has managed to run this and tell me what is the correlation they got. Nobody. Okay. So it's 0.83 or something. So whereas what you get before is, again, is the same thing. It's like 0.4, 0.4, and 0.3 for each of the different information signals in your data. When you combine them, you get something better. And effectively, what does this translate to? This translates to the fact that to estimate a demand at an area, you have to look at basically different users. So maybe some of the Uber users are part of the Foursquare community. Some of them are not Foursquare users, but they used to be, or they are yellow taxi users. And then, of course, the two services are under the sharing economy umbrella. So one might as well exploit Airbnb in this context too. That is it. I would like to announce a new version of OpenStreetCamp, the app that helps you find the cheapest taxi provider in the city, coming next month. We are also launching in London. You can find more information about what we discussed today on this paper. Follow us on Twitter, and thank you for your time.